Question 4, page 114, very challenging storyline, very difficult scale. The following graph shows the depth of water at the end of a pier over a weekend. Well, that's not hard. Now, to the right hand side, you may see I've worked out on the vertical scale, we've got 2 meters represented by these 5 little squares. Therefore, each little square is 0.4 of a meter depth. From 10 o'clock to 2200 hours, that's 12 hours there, from 10 in the morning to 10 at night. So I counted 24 squares there, so 24 squares is 12 hours, 1 square is half an hour. So with this in mind, we're going to proceed with this very awkward, clumsy question. It's quite hard to read off the screen as well. So first bit, at what time are the high tides on Saturday? Well, there's the first high tide and there's the second high tide. Now let's make this easy. If it was there, I've got 5 squares, which will be 2.5 hours after 10 o'clock. I've only gone 4 squares, so that's going to be 2 hours after 10 o'clock. Therefore, that's going to be midday. So 12 o'clock, midday. Oh, it's hard to write, isn't it? Midday. And this other one's going to be 4 little squares before 10 o'clock at night, which is 2 hours before, so that's going to be 2000 hours. In other words, 8 p.m. Is that alright? What is the maximum depth of water at the end of the pier? So that's that just there, or any of these, just read them across. Now I've got 1 square above the 10. Now we agreed that 1 square is 0.4 meters, therefore I'm going to go for 10.4 meters. So that's the maximum. And the minimum, well, it's one of these, isn't it? I think it's between 1 and 2 squares, so it's between 0.4 and 0.8 meters. I'm going to go with 0.6 of a meter minimum depth. What is the length of time between the consecutive high tides? So between that time and that time, so these are 2 high tides I've chosen. So from 12 o'clock midday to 8 in the evening, we've got essentially 8 hours, haven't we? Now this is very difficult. Clara is on holiday and wants to fish from the end of the pier. She thinks the best time to fish is when the tide has been fully out and is on his way in. So fully out is right there, and fully out is right there as well. Okay, it's also fully out here, by the way, so right. And also here, so these are all fully out, and so here's the water coming back in, the depth increasing there, and thereafter around about 6 o'clock in the evening on Sunday. So here we go. Trouble is, she has to leave at 1700 hours on the Saturday, in other words 5 p.m. and go for tea. She has to leave at 12 midday for lunch on, so that's midday. Very hard to write, I'm sorry. Right, how much time will she be able to spend fishing on the Saturday? Right, so let me try and work out what time that is. Let's have a look. So 10 lots of half an hour is essentially 5 hours. So here we have 5 hours after 10 o'clock. That's going to give us, let's just take a good look at that. So 5 squares, 10 squares, 10 squares, 5 hours. That's going to give us at 3 p.m. So that's going to be what's that? What's 3? It's 15, isn't it? So 1500 hours, and so that's the best time to fish. So that's going to be 1500 hours, 1600 hours, 1700 hours is right there. Right, she has to leave right there, 1700 hours, and between 15 and 17 we have 1600 hours. Therefore, from what I can tell from this point to that point, if she has to leave at 5 p.m. 1700 hours, she's able to spend 1 hour fishing. Now let's try and do this difficult one on the Sunday morning. Right, she's got to leave at midday on the Sunday morning, so that's 8 o'clock. Keep adding on the hours. That's going to be 1 hour there, so that's 9 o'clock. Other 2 squares. So 8 o'clock, 1 hour, 2 hours, 3 hours, so 8, 9, 10, 11, 12. So The best time to fish is 8 in the morning on Sundays, it turns out. She's leaving at 12, so it's 1, 2, 3, 4 hours time, so she can fish for 4 hours on a Sunday morning. Alright, so there you go. Right then, Wendy, what's Wendy going to do? I'm dreading this next question. Wendy sails her boat from the end of the pier. She needs at least 5 meters of water to launch and to land her boat safely. That's an important number. She launches her boat at 11 o'clock on Saturday morning. Right, how long does she have before she will not be able to land her boat? So she's out. Right, so how long can she stay out in the water basically? She launches at 11 o'clock on Saturday morning. Now 11 o'clock is right here. Let's just get one of these little dooberies. 11 o'clock is too, it's really hard to read this. Oh no, 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 no. Very difficult. Let's just get rid of that. And that one as well. Very, very hard. I'll try and go freehand on this just to show you what's going on. Let's change colour, just make it really serious. So 11 o'clock is 2 squares after the 10, so we're looking at round about here. Right then. She launched at 11 o'clock, right, done. And that's on Sunday and Saturday morning. How long does she have before she will not be able to land her boat? She needs 5 meters of safe water. So 5 meters is going to be right here between the 4 and the 6. So let me just draw that in. It's about there. Right, how long we got from there to there? Essentially, I think we've got 1 square before 3 o'clock. So that's 2:30 in the afternoon. Let me just write down 2:30 here in white so it stands out. So 2:30 in the afternoon, or in other words 14:30. So let's have a look. So 11 o'clock to 2:30 is going to be 3 hours and 30 minutes. So I'm going to go with 3 hours 30 minutes. Right, so it's 3 hours 30 minutes. That was 3.5 hours. Let's check it. She needs to sail her boat from the end of the pier. She needs 5 meters to keep it all safe. She sets out 11 o'clock on Saturday. How long does she have before she will not be able to land it safely? Well, when it hits 5 meters, you've got yourself 3.5 hours to play with. So that's what I'm making that one. All right. If she arrives late, what is the next earliest time that she'll be able to land her boat? Well, the very next time is going to be dangerous. The very next time you're going to be able to have 5 meters to stay out, and then right there, that is the time you can come back in, sweetheart. Alright, so there we go, cut 5 straight across there, and if you look at that position there, I think we've gone right there. So what have we got? 5, 10, 15 little squares is 7.5 hours. So 7.5 hours from 10 o'clock. Let's just do some maths there. So 10 a.m. plus 7.5 hours. What time can we come in? That's going to be 5:30 p.m. Put it into 24-hour clock. Let's add on 12. That's going to be 17:30. Just check that. Times there. So one of these, I think. Right. The following graph shows the thinking distance in blue and the stopping distances in red for different speeds, and that's come from the Highway Code booklet. The thinking distance is the distance travelled by a car between the driver deciding to brake and then actually braking. So I think I'm going to brake now. In the meantime, the car has gone forward while you were thinking about it. Right, describe the pattern in the thinking distance. So what's happening? Straightforward really. The faster the speed, the greater the thinking distance. Greater speed equals greater thinking distance. Maybe I should write it in white on the other side here. See how we go. What's the pattern in the stopping distance? Again, obviously the faster the speed, do you want more distance to stop the car? Same again really. Greater speed equals greater stopping distance. That's obvious, isn't it? Well, plus the graph shows it anyway. Use the graph to find. Okay, I predict I'm going to use one of these now. Use the graph to find. Let's work in black, neutral colour. Right, the thinking distance for a car travelling at 40 miles per hour. So 40 miles per hour, we're there, hit it, and turn left. It looks like roughly 10 meters, doesn't it? So the thinking distance, if you're going at 40 miles per hour, is 10 meters. So let's just go 10 meters there. The thinking distance for a car travelling at 55. Okay, 55 it is. 55 is there, and we're thinking about braking. That's what this says. Oh, it's not much in it, is it really? Quite dangerous. Alright, so I went up there and across there, and I'm going to make that 15 meters roughly from my rough sketch. So 15 meters. The stopping distance now, let's change flavour to blue, I think. The stopping distance for a car travelling at 30 miles per hour. Right, so how long will it take to, if I'm going to stop in, let's read it again. The stopping distance for a car travelling at 30 miles per hour. Okay, 30 miles per hour stopping distance. So I'm going that fast, and how long will it take me to stop, actually stop? Quite hard to tell really. Put a little arrow up there and turn left. So 5 little squares is worth 10 going up in 2s really. So I'm going to go for 24 meters roughly. Using my little equipment here. The stopping distance for a car travelling at 40 miles per hour. Right, so I want to continue this little line, hit that if I can, turn left. I'm going to go with 38 on that one. So 40 miles per hour, turn left. It may even be 40 the distance, I can't tell. So I'm going to go for 38 because I can't really get the line to go perfectly straight. So it'll be 38 meters if I'm going at 40 miles per hour. Right, the braking distance is, this is part C. The braking distance is the distance between the thinking distance and the stopping distance. Right, okay. Fred said the braking distance for travelling at 60 is 2 times the braking distance for travelling at 30. Is he correct? Well, let's just travel at 60, shall we, and find the difference. So thinking distance at 60 is going to be roughly 18 meters, and my actual stopping distance is going to be roughly 74. So I've got 74, take away my 18, which is what's that going to be, 56 meters. That's my actual braking distance between thinking about it and actually doing it and then actually stopping. So in reality I've got 56 meters there. So read again. The braking distance is the difference between the thinking distance and the stopping distance. Right, so it's 56 meters. That's me doing things at 60. Now at 30 it's getting quite hard to read this because I've used it for other questions. So here at 30 miles per hour I've gone about hard to tell, 6 squares up. So that's going to be 2, 4, 6. It's really hard to tell. I'm going to go for 8 meters there, so let's just change the different colours, it stands out. So 8 meters. I'm waiting to find out what happens at the stopping distance. 8 meters is going to be about 1 or 2 squares up, 24. So I'm going 24, that's meant to be a 2 by the way. Take away 8 is going to be, what's that going to be? 16 meters. Fred said the braking distance for travelling at 60 miles per hour is 2 times the braking distance for travelling at 30. Is he correct? No, he's not. Look at that. There's a difference of 40 meters. 2 times 16 is 32. 2, you know, so it's not 40. It's not 32. It's 40 meters. So I think the point we're trying to make is the faster you're going, you need even more time and distance to stop the car safely. So I think, as you can see anyway, just look at the trend. This is pretty linear thinking distance wise, but as you get faster and faster, we have a curved relationship here. It's not a linear relationship, it's definitely curved, and therefore the difference becomes more pronounced as you go faster. Look how close it is at 20 miles per hour, but look how wide it is at 70 miles per hour. So you know, whilst Fred's thinking was linear, the relationship with stopping distance is not linear at all. So he is wrong, therefore. Alright, I think I better stop there.